Hi everybody, this is Tor Storley, and today I want to do a video about SQL extension to Oracle SQL called the model clause. This particular model clause is used within data warehousing framework along with analytical functions and window functions, etc. You can do some pretty sophisticated queries using this technique. So today we're going to take a look at it and let's see how that works out. Okay, so let's take a look at the specifics of the Oracle model clause. I have prepared a slide deck and I'm outlining a lot of the concepts relating to how this is constructed and the way you can actually work with it. And some of the examples are not specific to the model clause, meaning you could have solved them using other techniques. Of course, PL SQL is one way, or you could solve them perhaps with analytical functions directly. So some of these examples you could have done a different way, but we'll build on it and make it more complex to the point where it'll be very difficult to actually create a query that will actually perform well using some of the later examples in this segment. Okay, so let's get started. So I'm gonna go to my first slide here. So the Oracle model clause has been around for a long time. If you watch this, today is in April of 2022. And as you can see, it's been around for almost 20 years already. So that's amazing. It came out in 10G database version in 2003. The model clause enables you to work with relational data just as if they were multi-dimensional arrays. So it can perform spreadsheet-like calculations, much like you do in Excel, and it is an extension to the SQL language, and it's scalable, just like you find in Oracle in general. So what are some of the specifics of how to go about creating this model clause, the syntax itself? Well, because it's data warehouse-like, it follows data warehouse syntax structures, such as partition by. Partition by is when you actually organize your data into logical blocks. You might have, if you think about it in a spreadsheet, you might have a series of similar groupings. For example, you have a bunch of data that relates to one country or more. You might relate them to different product groups or years, etc. So that might be something you want to partition by, you group it by. Now, dimension by is another syntax structure, and the dimension by is where you list the columns that are needed for a specific cell, if you will, in a spreadsheet to make it unique. So in other words, it makes a uniqueness of the row. Measure is another descriptor, as you find in data warehousing terms, and a measure is basically a calculation. So it's a value that is either a constant value, or it might be a value that's been computed. So you find things like prices, weights, percentages, etc. And in Excel, you can think of it as the values in a column. There's also something called rules. Rules is basically equivalent to formulas or calculations you find in Excel. It lays out the actual formula to arrive at the calculated value. So it could also be a constant where you set a reference to a specific cell. And keep in mind, we're dealing with multi-dimensional arrays in Oracle, but in Excel you will have like cell references. But you either set it as a fixed value or you can set it as a calculated value. This is basically the model clause, what's possible and the settings in the model clause. So as you can see, you start with the word model on the top here. That's the first word you start with. Then there is some other stuff we'll look at a little later, such as a reference model. There is partition by, we just discussed that. Dimension by, which makes the row unique. Partition by will be the groupings you make. Measures will be the calculated or the constant values that makes a cell reference value. Then we had the rules, which is basically the formulas, if you will, or the statement that how to arrive at the calculation value or how to set up a constant value. Now what I've done here is, as you can see, I have some turquoise or blue-like, I don't know how it shows up on your monitor, but these are the default values. And in the model clause, if you can basically exclude reference to these words, and it will pick up them by default. So as you can see, return all rows is the default. Keep not a value is a default. Unique dimension is a default. Upsert is a default. And sequential order is a default. So that's the structure of the model clause. If you compare the model clause to a spreadsheet or in a workbook in Excel, here's how you can kind of think about it. Now, we have rows and you have columns. So here I got row 1, 2, 3, 4, 5, etc. And it continues down. And then you have column A, B, C, all the way through I. And then I have some headers. In this case, I'm referring back to my ongoing stock retrievals from Yahoo Finance. And in this case, I selected AbbVie and Tesla, just to give you an illustration. Now, when you retrieve this data from Yahoo Finance, in addition to pass on a ticker, depending how many records you're requesting, whether it's, in this case, I requested 5 days worth. So it came back with the dates, and I converted these dates from a Julian date into a regular date so you can see it easier. So if you look at this now, the partition, the groupings, if you will, would be, in this case, by ticker. So you got AbbVie, it repeats here 5 times, and then Tesla will be repeated, etc. I didn't include everything. I didn't want to make it too large here, so just a limited amount of data to show you here. Now, this dimension here is the date, but it's not a true dimension because in order to make this row unique, you need the partition value, the AbbVie, and the dimension value, the date itself. Notice Tesla also have 3/31/2022, but the combination of the partition value, the ticker, Tesla, plus the date make this particular row 6 unique. And hence the same thing in column B here with column A. So even though I didn't list the AbbVie as the ticker symbol with the dimension, I already listed it with partition. So you don't have to put it into the dimension value. Also note that all these green ones are measures, meaning either constant value or calculated value. When you get data back from Yahoo Finance, you'll get these open, high, low, close prices as fixed values. And in this case, those are just constant values that comes back from Yahoo Finance. However, in column I here, I calculate a value based on the previous measures. So as you can see, I calculate in the first row of 0.18913%. And the formula I used was this log formula of dividing the adjusted close, which is in G1, and divided on G2. So in other words, because I have the dates in descending order, I take today's adjusted close divided on previous day's adjusted close, and I take the natural log of that to get the what is called a continuous compounded rate of return, which in this case is 0.18913. So that is basically the layout of the model clause. Now here is an actual example, and I'm just showing you this ahead of time, so don't worry so much about the syntax yet. We'll go more detail into it. But this is what a model clause will look like. And in my case, the reason I show you this slide is because I had a dimension to be the date. However, the dates differed. And for my purpose of computing a rate of return, I didn't want to make it overly complex. So I changed the dimension value a little bit. So for example, if you look here, under rules, you have the rate of return formula, if you will. There's a word called any, which means it could be at any row position. And I order by the date in a descending order. I use a round formula because I want to round the results so I don't have so many decimals. And here you can see I use this natural logarithm function, the ln function. I take the adjusted close on the current value, meaning the current row I'm on for the date, and I divide it on the adjusted close for the current value of the date minus 1, so 1 row behind. Now obviously in analytical functions you could use a lag function here to do this calculation, or lead, depending on how you structured it. However, my point here is that I have, as you can see up here, I have the date time here, that's being the dimension. But for my purpose, that is not working very well when I want to do this computation here. Because if you look at the data, between the 28th and the 25th, there's 3 days, not 1 day. So when I do my calculation, I'm getting a null here because it's looking for 1 day, not 3 days. So that's why you see here in row 4, you can see 4 and 9 and 14, I'm getting null values. So that's not ideal. So I want to fix that a little bit by changing that dimension value. So instead of using the date as a dimension, I can change it to use row numbers as a dimension instead. And that's what I'm illustrating here by switching it from here to here. And by doing that, you technically speaking don't need this partition either, because every row will be unique. However, you can specify that new dimension by saying dimension by, and then you use an analytical function called row number over, and of course we partition by the ticker. So that will be AbbVie, Tesla, etc. And then we order by ticker. So all the AbbVies becomes into one group. And then I also order by date time. So as you can see here, that becomes this one here. So by doing that, I can give it a number, and then I can use that as a dimension value. So that's basically what I'm doing here. So when you look at it now, after I change that dimension here, you can see I have on row 62, I have row number over parenthesis partition by ticker, just the way I showed you. So that becomes the dimension. Of course, the partition stays the same. The reason the partition by, even though it doesn't really affect this because it will factor in the ticker, the way that will work in this case is that if you look at the groupings I have over here, partition will break each ticker into groupings and treat them as separate units in this multi-dimensional array. That means whenever you do this dimension, it will be specific to this partition. This group, the dimension then will be specific to this group, and so on. So you can technically start over again. Like you see, I'm starting over with these row numbers over and over here. 1 through 5, 1 through 5, 1 through 5. Because they stay within the partition, it's fine, because it becomes unique within that partition. There's also some additional benefit for doing it this way, in that when you have huge amount of data, which you typically do in data warehousing, by using this partition, the cost estimator in Oracle, and when it does the SQL query, it will group these guys, and if it can, it will parallel process them. So it becomes a lot more efficient to execute these queries. In the model clause, there's something called symbolic cell reference, which basically means that you take the dimension values you can use. So in order to identify a specific value, as I said before, you need to take the measure and you need to pass in what makes it unique. Well, in this case, it's the hire year and the employee ID for this commission. So these are the dimension values you need in order to make this rule unique to a row. So that's what a symbolic reference does when you actually explicitly list the dimension values, like hire year, like employee ID. If you don't do that, you will use what is called a positional cell reference. Here you see the same thing, but now I'm removing the word for the dimension hire year equal to, and I simply say 2002 because it's positionally. Because this hire year comes before the employee ID, the hire year can be listed and comma separated, followed by the employee ID. And that's what's called a positional. So here you have an example of symbolic and positional. You can also combine the two. So here you can see I combined it by saying explicitly hire year equals, and then just positionally I take the employee ID of 112. So that's symbolic and positional references. Now there's something called unique dimension. Now, what does the unique dimension do? Well, it ensures that the database will perform a check to make sure that the partition by and the dimension by results in unique values. So in other words, it performs a check, and if you don't have a unique, it will throw an error. However, if you have millions of, or maybe billions of records and you want to run this model clause on them, you might want to try to find a way of improving the performance. One way you can do that, if you're absolutely sure that each row will be unique, so each cell value will be unique, you can refer to it as unique single reference. And by doing that, the database will trust you and say, hey, okay, I don't have to perform this unique dimension check. I'm just going to run it. But what will happen is if there is an error, it will throw it at you. So you can see here the model clause, unique single reference. And if it's not unique, it will still throw an error, but it doesn't perform that check on everything to see if it is unique. Okay, another concept is how do you deal with not a value, so like null values. There's something called keep NAV, which is the default. So you, technically speaking, here I listed in row 19 in my screenshot. You don't really need to put that in there at all because that's the default. It's assumed. I just wrote it out there so you can see it. However, if you're going to use ignore not a value, then you have to explicitly state it. Now, if you use the ignore NAV, it will replace the calculated measures that are missing, or if they're null, with one of the following. So if you have numeric data type, it puts in a 0. If it's dates, you'll get a 01 January 2000 for the date type. If it's a string, you get an empty string. And null is for everything else. And as you can see here, if you compare these two screenshots, in the first one I say keep NAV. That means it simply return a null value here when it doesn't exist. So only one of them exists. The last one, as you can see, is the actual number. However, the other one ignores NAVs. So what happened here is that it basically puts zeros in because they're numeric. This column is numeric. And as you can see from the rule up here, 0 is for numeric types. Okay, another part of the model clause that you can specify is how many rows do you want to see and what kind of rows do you want to see. The default is return all rows. And as you can see in the screenshot, it says return updated rows, but return all rows doesn't have to be stated because it will simply return everything that you calculate in that query. Now, if you return updated rows, like you see I'm doing here, it only returns whatever rows has been updated. Unless you have the ignore NAV and or the unique single reference or the unique dimension clause, then this particular return updated rows or any of the other ones should be placed below these clauses. So in other words, here you can see I had a unique single reference. So the return updated rows will follow that. It will not be before. If you didn't specify any of the other two here, the ignore NAV or unique single reference, then you could put the return update rows right below the model clause because it will use the default for the other ones. So let's look at some rules, meaning formulas, or how you assign a value to these measures. Now in this case, as you can see, I have a rate of return calculation I'm doing, and I'm saying any, meaning whatever row you're on. And in this case, I am not sorting the data. I sort at the very end, descending, by symbol, which is the ticker, and the date descending. And by doing that, as you can see, the row number up here was created with no descending order. So it was really 1, 2, 3, 4, 5 for Abby based on the dimension here. So what happens is it computes the first row, which is this 1 for Abby, row 1 for 3/25, 2022. And it's trying to divide it on the previous date, which doesn't exist. And therefore, for row 1 here, it produces a null value because there's nothing to compare it to. However, when you get to row 2, for 3/28 for Abby, you take the adjusted close at 161.97 and you divide it on the current row's previous value, which is that -1 here. So the current value of the row number, which is 2 in this case, minus 1 is 1. Therefore, it becomes 161.97 divided on 161.33, and that becomes this 0.39592, as you can see here. 0.39 or 0.4%, it went up. And then you continue like this. So as you can see, for the 25th of every one of these partitions, you will have a null value because there's nothing to compare it to before that. So that's how you compute this rule. The current value then, as you can see from this formula here, is basically a function on the right-hand side of each rule. You can use it. And it returns the current value of whatever dimension column you're in. In my case, I'm inside the adjusted close. So whatever the current value of the adjusted close is, based on the dimension, which in our case is the row itself. And therefore it picks up whatever number is, and that's the rule. You can also leave it blank, the CV function, and it will simply pick up whatever the dimension is, so you can implicitly assume what it is. So if you look at the CV parenthesis or CV parenthesis row num, those are equivalent. All right, so how do you assign and calculate a measure? Well, you can use the any wildcard keyword, as you can see up here on the left-hand side. So if this any here, if it is positional referencing, and you might recall that positional referencing is implicitly assumed. So when you say any here, you assume a row number without specifically saying row num equal to whatever row number, which would be a symbolic. So positional, you can use the any keyword. If it is symbolic, meaning you say row num equals, then you have to specify it a little differently. That is when you use something called is any. So when you see here, use is any wildcard when you use symbolic referencing. And it can only be used on this left-hand side of this equal sign, meaning inside the left-hand side of the rule. All right, so let's look at some functions that comes with the model clause. You can use a case statement at the right-hand side, which is a Boolean test. So you can say case when what you're looking for is present, meaning it exists, prior to executing the model clause, then return a true, otherwise return a false. There's also a function you can use that does the same thing, but it's a function. So you're checking the cell and you see if it's existing. It could be null, but the question is whether it exists or not. So if the cell exists, then return expression 1, otherwise return expression 2. Then there's a third function that says present and env. And what that does is it says, is it present? Is the cell present? And is not null value. So there's slight difference between this function and this function. By this allows nulls, this doesn't. Let's take a look at a couple of examples. If you look at the rules here, you can see that up here, you can see these are the original data I queried out. And this is after you applied the model clause and the rules. So let's just go through this quick. So C2, I say row number is any because it is a symbolic reference. By referring to row num, you use the word is any instead of just any. Here I'm using a case statement that basically says, take the salary on the current row, and if it's greater than 4,000 and the salary for current row is less than 9,000, or if the salary for the previous row is less than 17,000, then just display the salary itself. And that goes into the C2 column. So starting at row 5 and on, you can see you get the salary just repeating here for those rows because they satisfy that requirement. For C3, for row 3, which is this, what I'm saying is if the C3 is present, meaning I'm using a Boolean expression, then take the salary 8. So in other words, if the cell for C3 is present, which you can see right here, it is, then just grab the salary from row 8, which is 4,800, and put it in C3, which is this one. The next one is C4, which is this one up here. I'm saying use the function in this case. Does the same as the one before, but use the function. So in this case, C2 for row 3, which is this one, happens to be null. But because we're using this present V formula, it allows nulls. And even if it's null or has a value, just return the expression 1, which happens to be the value from row 5 in C2, which is 9,000, and put them in C4, which is this one. For C5, I'm saying for row 3, use the same function, but in this case, check and see if the cell exists. Because I'm saying row is 20, there is no 20 rows here. It only goes up to 10. So that does not exist. And if it doesn't exist, I cannot return, even though it could have been null, but this row does not exist. So I cannot return the 5th value in the column C2, which would have been 9,000. Instead, I have to return a 0. So for C5, that's what happens here. I'm returning a 0 for row 3. For C6, I'm saying not null value. So this is not accept a null value. So salary 2, which is row 2, up on the original one, you can see here, for Nina was 17,000. So that exists. So it exists, and therefore grab the 5th row's C2 value and put them into C6. So that's the 9,000 you see here that comes from here. from 9,000 here in C2. Finally, I'm setting, because I'm doing sequential order, it will execute these rules in a sequence. I'm setting the salary for row 2 to null. You can see it over here, even though it was 17,000 in the original data. So here I'm using the same function again, and I'm saying, hey, if it exists, then show C2's row 5 value, otherwise show 0. Because it doesn't allow you a null here, therefore this salary 2 is null, so therefore it will not show expression 1 but expression 2. So that's why you see the final number in C7 returns a 0. And that's how those functions work. So the rules evaluation modes, we talked about it a little bit already, so it might be a little bit, towards the end here. But there's 2 modes for evaluating the rules. Sequential order, which basically they execute the rules in sequence, and automatic order. That's when the rules may be dependent on one another. So there might be a previous rule that are depending on a later rule, and if so, Oracle would generate a dependency graph in order to solve that problem. So here you can see the 2. This is not necessary to say rules sequential order. You could have just said rules without the sequential order. However, for automatic, you have to specify it. So you have to say rules automatic order, as you can see the second screenshot. Because it's executing sequentially here, you can see this C2 for the row num happens to be using the second formula we just looked at. They don't accept the null value. So here we say in salary 1, which is row 1 salary is 24,000. If that exists, display salary 2, which happens to be overwritten in this case. You might recall back from the previous slide, this one had a value of 17,000. Because I've been running this, it's a little misleading right now. This should have sent 17,000 in the salary here. And that's why they show 17,000 here. The second one has automatic order. Therefore, salary 2 gets set to null, like this, even though it's the second rule here, because it's automatic. Because the first rule is dependent on the second rule of salary 2. Therefore, when you do that, it becomes null in this column instead. You can do looping inside this model clause. So that allows you to do PL/SQL-like for loops in this clause. Now, when you do, you can use these kind of formats. You can say for some value representing a number, and you can choose a subquery, so you can actually write a query here, or you can just list a list of values here. The second method could be, say, for v some value and using a like pattern. And then you can say from value 1 through value 2, and you can increment or decrement the values. The third way of doing it is for k2 in some multi-column subquery or multi-column list. Now, in order to get more details about this, because it's very exhaustive, you should probably refer to this Oracle Data Warehouse Guide. And in this case, I chose 19C because that's supposed to be the stable version. 21C is more experimental version that some parts might be used in 19C, but more likely they will be used in the next version of Oracle Database, which will be 23, I believe. In any event, I have a link here, and this is the section you want to check out in order to read about this. You can also do interactive loops, or I should say iterative loops, not interact. This only works with sequential ordering, so you cannot use automatic ordering, but it allows you to evaluate the rules in a loop format. And here's the format for it. Iterate the number of iteration until you meet some kind of condition. And again, I set a reference here to where you can find out more about this particular syntax. Here you can see I have an example of creating iterations. I'm using the sequential order like we said. I'm going to iterate 6 times until the running total, which is this, let me get my laser here, gets greater than 70,000. This is the rules that I'm using. And notice I use iterations, iteration number. So iteration, I create some measures here. First name, last name, salary. They were already in the query. But then I added these iteration and this running total measure. And I just created null values initially and as numbers. I populate the iteration number, which is built into this iteration routine. You get the number. And I put it into this iteration column, which is this you see over here. Then I have a running total. I set it in row 0 here. I set it to 0. So it starts at 0 here. And then For row 1, I'm saying salary for row 1, which is Steve King, 24,000. Set that here, 24,000. And then for the running total, and then I do a loop, I say for row num in 2, 3, 4, 5, 6. So that's kind of a in clause I'm using, do the for loop is. And I say, hey, take the salary for the current row, add the running totals current value minus 1. So if you look at the running total now, you'll have the salary for row 2, which is this 17,000. That's the first one that happens. Take 17,000 plus 24,000, and that should give you the running total. Yeah, the running total of 24,000 plus 17,000 is 41,000. Then you take 41,000 plus 17,000 is 58. And that increments based on this iteration number here in the for loop. And it says, do it 6 times or until you reach 70,000. Right here in row number 5, which is basically 0 base, so it's 4, I'm getting into 70,000. So it reaches us here. So this is the last iteration number. After that, it just stops going here. If you try to do it automatic order, you can see here, you're getting iteration error. So that doesn't work. The execution order, the model clause executes pretty much last, meaning your query will run to get the data, and then the model clause will be applied over that data, and finally the final select and order by will be executed because you'll be selecting certain fields, measure fields from the actual model clause that you will display finally. You can have the model clause aliases that you used, but you can also recreate new names for those aliases again in that final select statement. And that's what this is saying, the second paragraph. Okay, so if you look at how that could possibly work, you can see here, I'm creating a partition by, I say ticker symbol, row number, I name row num, date time, I name DT in the measures here, open, and so, which is the same names. I got this rate of return down here. So up here you can see I'm changing the date, the DT from here. I'm changing even from the original date time to DT in a measure here, and then finally into date. So the final result set here in the select statement is the word date. So that's how I'm coming up with the alias of the alias, if you will. Now, finally, there's something called a reference model you can use. That means you can actually, within the model clause, you can have another model clause that refers to different tables that you want to include in your main reference model. But you can refer to multidimensional arrays from another table if you want to. So it becomes more like a lookup table within the main model clause query that you're using. And again, I have a reference here you can go to find out more about how to use reference model and more of those details. Why should you use this model clause? Well, if you build applications with a model clause, you can replace spreadsheet-like functionality. So from other external computation engines, like taking data out of the database and putting into Excel, for example. It's more robust and efficient solution. Think about it if you have a lot of data, millions of billions of rows even. Why would you take that out of the database and try to put it into a tool that may or may not be able to handle it, like Excel? So you can do some advanced calculation directly in the database with good performance because it's SQL-like. So it has all the capabilities of a SQL query. It's very scalable and manageable. And also, it's more secure because you don't take the data out of the database and give it to some random user somewhere so they can have the data. Perhaps you want to keep the data secure, you want to keep it centralized, and you don't want the user to start changing structures and come up with new data insights that doesn't necessarily match what you have in the data or data warehouse, I should say. It's more secure that way by keeping the data in one place. You keep it inside a secure database. Again, you don't have to transfer it into these modeling environments, all this data. You can also share it across workgroups, and you have one version of the truth, if you will, because everybody runs it the same way, so they don't start making up their own versions of how to compute these models. So it has a lot of advantages. And I said before, by doing parallel processing, you like partitioning and what have you can get very good performance and very efficient calculations. Best of all, let's say you can't really write PL SQL queries or procedural language SQL queries in Oracle. You may not have the rights to do it. It might be restricted from you to do so. And therefore, you can write a SQL query and execute it in the database and get the same results out without actually have to do all the overhead of PL SQL. Now, why should you not use it? Well, it takes a lot of effort to try to understand it, for one, as you probably have seen. So it's not for the meek, let's put it that way. It takes effort, and it takes some know-how in order to create these queries. If you don't require it to do it, for example, that stock example I gave, I could probably have done that fairly easily using just analytical functions by doing a lag function of sorts. However, I just wanted to show you how you can use the model clause, and I try to keep it very simple. But if you can use other methods, you probably should, because it has more overhead, obviously, when you use this model clause. It can use more resources because it takes a lot to build these multi-dimensional arrays and run these queries over it. So it might require some more resources to do so. And it has limitations. For example, you're applying subqueries on the left-hand side of a rule in a for loop. You cannot correlate it. They cannot be correlated. You cannot define it with a with clause. And you can only have about 10,000 rows. So there are restrictions on how to use this. Okay, next we're going to be looking at some demos that displays some other examples of how you can use this Oracle model clause. I'm going to check and see if the cell reference existed prior to executing the model clause. You can see I have my original query here. So if I run that, you can see it brings back the original data like this. Here I want to go against this CTE, or the common table expression, and I want to query out some measures that I'm generating below. The dimension is by row number, based on salary in descending order, so it's based on this column here. I create two new measures, row existed and row existed positionally. And I simply set it to a varchar 10. I'm running in a sequential order, so each rule will be executed in order. And then you can see here, from the salary column, I'm creating a new row, 110. And that row does not exist because there's only 10 rows in here. So that's a new one. I'm setting equal to null, and I'm setting salary for row 8, which is this guy. I'm going to set that equal to null. And then I have a aggregate function here that's going to sum up the salaries, but only where the row number is between 2 and 6. So I only care about the salary for these rows. And then I have a row existed. One of the points I'm making with this query is that you can say row number is any. That is equivalent to using a symbolic referencing. And if for symbolic, as you might recall, you have to use is any. So what I'm saying here, a case statement, when salary for the current row you're on is present, and that is that test you're doing, that's function, if you will, or the expression. If it is existing, then say yes, otherwise say no. And then I do the same thing here, but I use a positional referencing now. And for positional, you have to just use any, not is any, because there's no symbolic reference here. Same thing here. I'm going to run it twice under two different names. So if I run this now, you can see here's row existed, use a symbolic reference. Here is row existed, positional reference. You get the same result, any versus is any. And again, this for row 9, which is this one, I sum up the rows for salary between 2 and 6. Okay, you can also run analytical functions in the model clause. So you create aggregate function only on the right-hand side, though, this side. So here I have another query that goes against this view. So here you can see the data. So there's a few fields: employee ID, job ID, country, first, last, salary, job title, and so on. So there's some data in this view. And what I'm interested in doing is to compute some analytical functions on the top of this data. So I create the measures. I'm dimensioned by the employee ID, this one, and partitioned by country ID and job ID. So it'll be country ID All the US would be one partition. Here I'm just creating two new measures, and I set them equal to 0 because they're numeric. And here in the rules, based on these two new measures, for whatever row you're on, any, in this case we're using positional referencing, I'm going to use the rank function, which is an analytical function. I'm going to do it over order by country ID and job ID and salary descending. So I'm going to order by highest salary for whichever country's job ID that had the highest salary. So I'm sorting it that way by giving it a ranking. Then you can do a dense ranking, which is very similar to ranking, except for ranking will skip a number if it has two of the same. Dense rank will just continue after it's done. So here I'm going to order by a few fields. So let's run this. All right, so now you can see here's the ranking. So if we choose the UK for sales manager, for example, ranking was based on 14,000, 13,500, 12,000 for salary. 1, 2, 3, 4, 5, as you can see. Dense ranking was the same here because there was no repeating. But if we go further down here, and if we look for something that might be repeating, like the sales representative, for example, notice here, this one was 8, and then the ranking became 11 here. So it skipped a few because it had repeaters here, so it skips what it does. Here on the dense ranking, it just continued the sequencing. So there's a slight subtleties here in how that is applied. In the third one here, I'm using a basic aggregate, and I'm also using for loops on the left-hand side only. So if you look here, without repeating too much here, you can see I have a running total, iterations, and a max amount, count rows. I have the dimension is the row number over salary descending, and then I create all these new measures. What I'm doing here is I'm running sequentially, because remember you get an error if you run automatic. I iterate up to 6 times or till this running total iteration number is greater than 15. So here I'm simply setting the iteration number. Here I'm setting the running total in the first row equal to salary, first row. And then I have some additional fields here. And some of them doesn't exist, like these. So they be added because the upsert all will be used as a default. Then we have a first and last name I created for row 100, which doesn't exist. Here I'm using a sum of salary between certain row number sequence, 7 and 9. And here I'm using a for loop, and I'm using an in clause. So I'm saying for row number in 2 and 3, then run this rule. Here I'm doing a mod function where I'm specifying even rows only. So I say row number, and I'm saying with mod 2, and this expression is equal to 0, that means you're getting the even numbers. And if it is an even number, then take the max of the salary in the row between 1 and 8. So it's fairly complicated. This is not something you would easily do in a select statement. So let's run this. And as you can see, you're getting all these results. You can see the max amount is going on the even rows here. And here's the new row that didn't exist, and we added all these values in. The count rows, the iterations was up to 6. And then, because then it turns out to be greater than 15, the running total. You can see you can count rows here. And that's this one for row 9. Okay, it gives you the count of row numbers between 3 and 8 for the salary, 6. Okay, so that's why you set a 6 there. Okay, so this fourth demo here introduces this reference model. Now this is a little detailed, so without exhausting this query here, I'll just try to highlight some of the keys here. By the way, this employees table here is coming from the HR schema in Oracle. So if you install the HR schema in Oracle, you should have access to this table. I'm creating a model clause, but then I'm using this unique single reference. I reference this FX rates table. So if you look at that, that is the exchange rates. So currency exchange rate, inverse exchange rate, and FX date. That's this table here. So it has an exchange rate for each currency type. So let's see if we can find an example. So I happen to know that the Norwegian kroner is about 8.837 when this was taken, which was the 8th of January in 2022. There was 8.837 kroners in $1. And this is the inverse when you take 1 over this number. So that's what that one means. We got the exchange rates. So I'm selecting these type of currency. So if I run this, you can see I'm only selecting a few currency, not all of them. So these are the ones I'm basically querying out here. I'm dimensioned by currency inside this reference model clause. The measure is exchange rate because that's what I want to use. In the main model clause, I'm going to dimension by row number over the salary column in descending order, which we've seen before. Here I'm creating some artificial measures that I'm going to be computing. So we got salary for euros, for Saudi Arabia Rial, for Japanese yen, Great Britain's British pound, and of course Norwegian kroners and so forth. So here you can see some of the measurements. I use the sequential ordering, and here is the rules. The rules are referring back to this reference table, the lookup table for exchange rates. And I'm basically grabbing that table and I'm grabbing this field from that table. And because this is a measure, I'm referring to this salary Norwegian kroners for the row number would be equal to this rule. Once I've done that, I will show you the exchange rates that I used by loading those in here for row 1 only. So let's run this and see what it does. So here you can see, here I'm getting it back. So you get the original salary dollars for each one of these rows. Here it is in Norwegian kroners after you applied the exchange rates to it. So as you can see, and here is the exchange rate that was used for each one of them. So it allows you to do inter-row calculations based on the current value of the row times those fixed values, as you can see here. So that's a more involved query. Finally, what I want to talk a little bit about is the optimization of the model clause, what you can do to try to make it more efficient. So I created a couple of slides to try to demonstrate that. In order to figure out how well your model clause is performing in a query, you need to probably take a look at the execution plan. And if you look at the execution plan, you're going to find 5 types of algorithm that the model clause will be using. It's acyclic, acyclic fast, cyclic, ordered, and ordered fast. When you use the automatic order reference, it will be using the cyclic or acyclic algorithms. If the rules themselves are not cyclic in nature, it will use acyclic. But however, if the earlier rules depend on later rules, it will probably use a cyclic type of algorithm. If you use the sequential order reference, meaning the default, then it will use the order type of algorithm. If there is no aggregation for the individual cells, it will either use the acyclic fast or ordered fast algorithm. Here is a screenshot of a query run. You might recognize this from the earlier queries we did in this video. But here I'm doing explain plan 4, and then I have my query, including the model clause. And then I run the query with the explain plan. And then after I'm done with that, I do a select from table function where I call this DBMS XPlan system package that has a function called display in it. As you can see, the query returns some results on the bottom there. When you look at the result, you can see that I copied it over into a notepad, so you can see it on the top there. It produces the explain plan for that particular query. And the way you read these explain plans is from the latest innermost outwards. So table access full for the stock table will go first. It grabbed 15 rows and it tells you the cost and the bytes it retrieved and the time. And then it ran the model clause using the ordered method. That's because if you look over under the model clause, I don't use automatic rule here. So use the ordered method, the algorithm I should say. And then it goes ahead and sort it. And then it finally does the final select out of that. So that's how that particular query runs. Here is a second version of a query. Here, however, we are running a inline view. So if you look at line 5, it says select star from parenthesis, and then the actual model query is inside the parenthesis. And then finally at the end, we order by symbol, row number descending. So when you run that explain plan for that query where we have an inline view, you can see it produces in line ID2, I should say, view, the word view. And that is because it's using this inline view where you select star from, another query. And that's why it gives that idea of view. Now, here's a third query, and here we are using the default sequential rules. And in ID3, you can see in the explain plan in the notepad on the side there, it uses a SQL model ordered, as you can see. And also because our dimension in that query, as you can see in the red outline there, the dimension is using an analytical function for the row number function. So you can see in ID4 on the explain plan, it uses this window sort operation because it uses that analytical function in the dimension. And that's why you see that window sort. You can also try to give the query hints. So here I run a CTE and I use a parallel hint. And this is probably something you want to try to do if you have many cores you can run it over, particularly when you have partitioning. So here I tried just to illustrate that, but as you can see from the result, I don't really have a lot of cores to run it over, so it gives me this message. But that's another thing you can do. You can try to run a parallel. There is more to this, obviously. There is something called predicate pushing, where you have an inline view. You are outside the inline view where you do the select star from some query. You use a where clause. If you referring in a where clause to some kind of reference to a partition that you filter, the idea is to push that into the inline query itself, so you reduce the number of rows, and that will make it a lot more efficient. Now, for some of the dimension values, this may or may not work. I just want to mention that predicate pushing is very important as well in this execution. I don't really have an example for that right here, but you can look that up on your own. All right, I hope you liked this video. I'm going to wrap it up here, and I would just say thank you for watching this video, and I should see you again soon, I hope. Take care.